Hello everyone and welcome to Handmade Hero, the show where we code a complete game live on stream. Last week we finished up our port of the Handmade Hero lighting engine to work with cube-based lighting, which is a step that I wanted to take so that we can start to work on performance optimizations of the lighting scheme. And that is exactly what I wanted to start working on today, because we have some sort of work we have to go through to figure out how exactly we're going to try to accelerate the process of lighting inside Handmade Hero so that we can scale it to very large levels. And fortunately for us, when we're talking about lighting in Handmade Hero, we're not really talking about lighting the whole world at once, because the whole world could be, incredibly huge, and there's no way we're ever going to compute the lighting on the whole world. But fortunately for us, Handmade Hero, we're not trying to do that. All we're really trying to do is compute the lighting on a small subset of the world, a subset that we can see. And so in order to do that, we kind of need to just take the light area that we can see and perhaps a region around it a little bit, so that we can capture light coming in from the sides as necessary through doorways and such. But that's really all we're talking about. However, even just that local region has way more stuff in it than n squared would allow us to really do, because n squared algorithms obviously have very bad performance scaling. So even getting up to a couple thousand lighting elements, let alone 10,000 lighting elements, well, that's not a particularly hard problem. If you have a linear algorithm, 10,000 elements might be fine. N squared algorithm with 10,000 elements is not going to fly at 60 frames a second. That's just not really feasible even on today's fast hardware, as long as you're doing anything non-trivial. And the reason for that is pretty straightforward. If you take a look at what 10,000 squared is, you can see that it's proportional, right, to... Is there any way to get this thing to put commas in, by the way? Looks like not. I find it easier to read numbers when there's comments in them. Oh, yeah. Yeah. That's what I'm looking for. I don't really need comments, just something. Okay. So anyway, if you take a look at what happens if you take numbers as large as 10,000 and you're doing an n squared algorithm, then the number of things you have to do to make that algorithm complete is proportional to an extremely large number. In this case, we're about 1/10 of a billion here. And one of the things that you have to remember is we're working on machines that are around, say, 4 gigahertz worth of speed in the case of a CPU, less in the case of a GPU. So in that case, right, we're talking about something like this. And if you look at those two numbers together, you have about 40 of these that you could do in here, just cycles of the processor, right? This is 4 billion cycles. That's how many I do per second. And if I'm doing 10,000 squared operations, then even if each operation was only one cycle, which is not realistic, then I'm getting into a situation where I'm not even a multiple of 60 away from my total number of cycles per second. And remember, so at 60 frames a second, this number drops to here, which is already less than this, right? So our total number of work units that we're going to have to complete is less even than the number of cycles per frame, in this case at 60 frames a second, that we're doing. Just by comparing these two numbers, you can instantly see why squared numbers are really bad in this scenario. Now, on the other hand, if we took a look at the unsquared number, which is just that, you can see that there's plenty of headroom in a number like this for a number like this. And so just in your head, having that sort of basic back of the envelope ability to see n squared algorithms really top out early in a video game scenario because of that incredibly tight cycle budget that you get at 60 frames a second. It's just not feasible to really work on things that are n squared in that way. So what we're looking for here is a way to linearize, to the extent we can, the lighting computations, so that, for example, we only have to touch every element once instead of a squared number of times. That would be great for us. But the question is, how do we do something like that? And so what I'm suggesting that we would need to do in order to make this work is to try and get into some kind of a log space where we're doing things on trees of grouped elements, for example, so that we can, instead of processing every element once, which would be optimal in this case, we can maybe process the number, each element once, plus some sort of low amount of additional transport work that's not proportional to the total number of items linearly, so it doesn't go n squared, but rather proportional to the total number of items, say base 2 or something like that, right? So again, what we're trying to do is figure out something like that. This is exactly akin to something, say, that you would normally do in any other kind of algorithm. If you have an n squared algorithm, but you feel like, oh, if I sorted the elements, then I could do something with them that was linear. Well, the sort is n log n, and then the operation is linear, it's n. So that would get you down to something that was pretty much acceptable, because log n is a very small number, so multiplying n by it is not really a big deal. So something that's proportional to 2n log n or something like that is really not a bad algorithm at all, and would be totally feasible. On the other hand, n times n is totally unfeasible in our case. So again, we're just looking for a way to break that squared piece there, but we can do other things like loop over the all the elements a multiple number of times. That would be fine as long as that multiple is a constant, 2, 3, 4, 5. That's probably not a big deal. And we can throw in a log in there. That's no big deal. So we've definitely got room to maneuver, but we just can't go n squared. So that's all we really need to do in order to get us to a place where we can be comfortable with it. So let's talk about some basic aspects of what we're doing, and see what we can do with respect to coming up with a sort of plan. I sketched one out the other day that was involved sort of aggregating things up into bigger cubes. And that doesn't seem like a particularly bad idea. Let's talk a little bit about maybe the most straightforward way to do that. And maybe we can try something like that today. So one thing that I talked about before was that, well, if I have a lighting element, which is a cube here, and it's got these points on it, and I'll just draw these in 2D for now because it doesn't really matter. The scaling out is going to be similar in either case, because as we group things together, it doesn't matter whether we're grouping them in 3D or 2D really, for purposes of thinking about the problem anyway. So if I have some lighting elements and they look like this, then normally what I'm doing is when I cast a ray out, I have to look at every single one of these elements, and that's really the problem. So if I have n elements, and I know the number of lighting points is going to be some number, whether it's, I think it's like 24 or it's some constant times n, right? It's how many of these cubes I have. Then basically what I'm looking at is I have 24 times n times n, because every time I cast one of these rays out, and really there's even another value in here, which is r, right? Which is also a constant, which is the number of rays cast. So it would be 24 times the number of rays cast times n, which is the number of total rays that I would be casting, times another n, which is how many things I have to intersect with. And you can see why this number gets particularly bad. Well, this number right here might not be awful, right? 24 times, I don't know how many rays per frame we want to cast, but let's say it was 32, times n. This might not be the worst thing in the world. We may still need to cut that down, because 24 times 32 times something like 10,000 is still a pretty big number, right? But even that, in theory, we could probably fit inside a frame budget of something like this, because don't forget, something like the number 24 or the number 32 is something that we could cut down, those constants. We could cut them down by multi-threading, first of all. Remember, we've got 8 threads potentially to work with, and SIMD, which gives us a 4 wide situation to work with as well, or potentially 8 wide as well, right? So we could get as much as 64x of a speed up here, which makes this look not as bad. This is unrealistic, of course. You rarely get a full 64x speed up. So, but even if we only got something like a 16x speed up, then 24 times 32 divide 16, right? That makes this just 48, which is a much less problematic number to look at if I did that math right. So we're looking at more like 24 times 32 times 10,000, but divide by 16. And, you know, this is a much more tractable number, right? So, you know, when you just have constants in here multiplying it out, you can fight those constants with sort of our standard optimization techniques. And also on a GPU, the same would apply. GPUs already employ plenty of SIMD and multi-threading automatically. So if we were to drop this into a shader, the same would apply. A huge divisor on the constant here, which is actually why GPUs are so fast, right? They don't do anything your CPU doesn't do, really. They just have a ton of compute units sitting around that can be issued in parallel. And since rendering is highly parallel, off you go. So, just want to give you a breakdown of that analysis there. So really the problem is this, that we want to start attacking first. And we can worry about attacking this later because this is a little bit more of a standard optimization problem and we have a lot of things we can do to try and make that work out. But this right here, there's nothing we can do. So standard non-algorithmic optimization is not going to help us with this times n, and that's what we want to attack. So as we're casting these rays out here, what we want to do is take a look at what we could hopefully try to accomplish to take something that was an n, so there's all these lighting elements out here, and we're looping over all of them. And we want to reduce that n number to something much smaller, right? So like I said, a log n might be nice, something proportional to a severe reduction in the n count. So the most basic thing we could do here is a standard acceleration structure, right? So raycasting in general, typically what it uses is some kind of acceleration structure exactly for this purpose. And what those acceleration structures are things that break the arrangement of things down in some kind of spatial way, such that when you raycast against them, you only test things that could possibly hit the ray. For example, let's say we've got all of these light elements out in space. All of these things are little cubes, let's say, that could intersect any of our rays, and they're just all over the place, right? And there's just a ton of them. And so then we go casting a ray at one of these things, and we know that the ray is going in this direction. Well, you can see even just from your own intuition that if you were going to narrow the search space down here, you could probably do something pretty straightforward visually yourself, where you just go, well, none of these things out here are ever going to be relevant, because since the ray narrowly goes in this, you know, sort of shaft through space, any of this stuff that's clearly outside of that region of the ray is just not relevant and shouldn't bother to be considered. So if I had some way of quickly sort of bucketing these things as not being relevant, that would do a lot of work towards eliminating them. So that's where the notion of an acceleration structure comes from. It says, what if I grouped these things up into pieces so that I could eliminate whole chunks at a time and never loop through the sub-elements of them to check them for intersection of the ray, right? It's basically saying, let me have some larger element I can use, and we'll do that. So for example, in this situation, let's suppose that I had grouped them in some chunky way, like we've got these and these and these over here and those and those and those. Then when I see this ray, I know that if the ray only hits this and this, that I never need to loop through any of these. So instead of checking each of these individually, I only check 1, 2, 3, 4, 5, 6, 7 of these. I just do 7 checks instead of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, instead of 15 checks, and I've halved the number of checks. Furthermore, I can continue this process, right, of grouping it up further. And here I will just do 3 checks at the head end and then start looping through these other ones. And so I can eliminate all of these and never do even these 3 checks at all by just doing 1 check or something like that. You can see how it gets more and more powerful as you group into coarser and coarser pieces. Now, what's more is we can make other assumptions about this once we actually get to the point where we've got an acceleration structure in place. There's also some other things you can do that don't reduce the worst case n, but do reduce the best case n, which again can give you a further speed increase. It's not clear we want to necessarily do that, but we could. And what that is to do ordered traversal of the acceleration structure. The way that that works is that, let's suppose I had a situation exactly as you see here, where I've got two spatial partitions of some kind, whatever they are, and they have a bunch of elements in them, and the ray is going through those like so. In this case, what we know is that if we processed these in a biased order, so we processed, if this is A, we processed A first, and then we processed B, right? If we process A first, we know that if we hit something in A, we don't need to process B because all the elements in A come before all the elements in B. Another way of saying this is that if we have a bounds on this structure and we know when the ray enters the structure, we will then know the t-value along the ray at which the ray enters a particular bounding structure. If the intersection of one of the points in A that we find, the best one, if that is prior to the t-value of entry into B, then we know we don't need to test it. That way, even in scenarios where the ray enter and exit points may be misleading. So for example, if I had a spatial partition where there was some way of crossing the partition earlier, so I'm trying to see how this, so let's say we had overlapping spatial partitions that looked like this. All of these X's are in this one, and the O's are in this one, right? So if we wanted to have overlapping spatial partitions and I cast against them, and I see here that I have, an X that I am checking against here and an X here and whatever, and maybe it's this X that I hit. Well, this O technically comes before this X, and maybe the ray actually hit that one. What that means is that if I check this A first and this B second, I will find a hit on A, but I can't necessarily not check B because I have to know whether I hit this one or not. Again, you can even do it in that scenario just by having a notion of when you possibly entered B and whether that is always after the greatest hit you found in A. So in either case, we can always determine whether we need to continue traversal or not, and that can get you an extra speed increase as well. Another way of stating this kind of a problem, and the kind of thing that you'd see in more of a space partitioning tree, like a KD tree rather than a bounding tree like a sphere tree or an AAB tree, is that if you have something like a KD tree which just splits elements, then you really don't know much about when you are traversing your elements. You may not necessarily know specifically, although I guess, well, no, in this case you do still know in a KD tree because KD tree is not loose. If you had something like a loose KD tree, which I guess would actually not be that uncommon in the case where you don't actually split elements along the tree boundary, which we probably wouldn't. If you have something like a loose KD tree, then you've got the same problem because here's like a KD tree example, and if we have things in there that span across two different nodes in the KD tree, then when you end up with a situation where you've got, say, this, for example, is sorted into this node. What's a good... I got to create a scenario here that's actually going to demonstrate what I'm talking about. This will do it. So let's say this is in node A, and this is in node B, right? So when I cast here, what I'm going to find is the ray starts in node B, so I would start by checking against the elements in B. I would find a hit on B, right? B would be the element that I would hit first. Now, if I therefore stopped checking any other of the nodes, I would be in trouble because I don't actually know that I hit A, which is kind of overlapping into it, right? So if you have a tree that happens to be loose, you've got extra work to do because you have to know whether or not the bounds of this thing actually extend inside or not. And I'm not really sure, to be honest. I've never really done much work with a loose KD tree, so thinking it through right now, I'm not even really sure exactly how you handle those things. Maybe you push the boundary of the tree out to the largest element in either case, so you actually have two bounds on the elements. I'm not sure. I feel like traditionally KD trees and BSP trees, you always split the elements. So for example, if you have an element that's sitting across the boundary, you split it into one on each side, or you just have a pointer on each side to the element, so you always would have the element in each. So I'm not sure it's really a relevant concern, because I don't think I've ever seen it done that way. But either way, I just wanted to get the point across that you can always kind of determine the information you need to know for whether you can safely early out or not. You just have to construct your raycasting algorithm to make sense of it, I guess is what I'd say. All right. So there's a lot of ways, like I said, we could do this, and I'm going to talk a little bit now about which way I'm going to do first and why. So something like a KD tree is traditionally what you would use for raycasting a scene if you're talking about actually raycasting the scene. The reason for that is because it does the sort of the minimal amount of work per step necessary to eliminate some elements, and that tends to be the most useful thing. So KD trees are very popular in ray tracers that are actually trying to do ray tracing of the whole scene down to a very high level of accuracy. However, I'm just not sure that something like KD tree is exactly what we want, and the reason for that is I don't think we're interested in actually ray tracing the scene. What we want to do is get approximate lighting from stuff that's far away and accurate lighting from stuff that's close. And that's why I think more of a multi-resolution tree may be more what we want. And that's why grouping, I think, is a little more useful here. Because what I would like to do is not actually traverse the tree. What I would like to do is say, okay, let's suppose we've got a bunch of coarse lighting elements here that number in the very small numbers, like 5 or 10, right? And then when we cast a ray out of one of them, let's say we're computing lighting for things in this region. We've got a little lighting element here that we're computing, and I want to cast a ray out of the surface of that, and it goes in this direction. Well, the elements in here are obviously very relevant to that because they're very close to it. And so I'm going to expand this tree down pretty coarsely, perhaps down all the way to the bottom where we've actually got individual lighting elements, and I will collide against individual lighting elements. But what I would rather do for stuff out here is just treat them all as one big aggregate lighting element, right? I would rather not even traverse the tree. This is what I mean when I say that I want kind of a coarse lighting approximation. Excuse me. Because I really just don't want to focus at all on this part of the problem, right? I don't want to try and get accurate hit detection way out here. What I would rather do, because again, I'm just spending a lot of time producing individual hits about specific lighting elements in here when those lighting elements are not really that relevant to me. All I wanted to know is, generally speaking, how much light is coming from this area. So what I'd rather do is build up these trees sort of in some way that gives me aggregate lighting elements that say how much light is leaving that region in the general case. And then when I do lighting and I gather the lighting from external areas, I want to just go, okay, tell me roughly how much light is coming from this area, and I will use that amount for any ray that makes it this far, because I really just don't want to know about every little piece of minutia. This would not be what you would do in a non-real-time, in a thing where you were interested in computing very accurate lighting. This becomes a problem because maybe what you were trying to do is capture some very long shadow cast by something over here, and in a film rendering scenario, you want all that information. But we don't want that. What we want is a general idea of how the lighting is flowing through the scene, and we don't really care whether or not that lighting is accurate. We care whether it is plausible and feels good in the space at a high speed, right? So we're trying to come up with approximations. This is crucial. We're trying to come up with approximations of how much light would come from an area so that we don't have to spend all of this time ray tracing all of the individual things in the area to figure that out, because we know ahead of time we're not going to be able to cast enough rays to do that. If we were, no problem. But we know ahead of time we're never going to radiate this area with enough rays to really figure it out. So instead, let's figure out how we can get a coarser estimation, and I think this is the way to do it. So what I want to do is I want to start by doing something where individual elements can be clustered up into larger elements, and those elements can have their lighting considered in aggregate as if they were just bigger elements, right? That is what I would like to do. So, there's a lot of ways we could try to do this. Since our game already has sort of the concept of a spatial partition in the world in general, I think we could probably do some kind of leveraging here where we can lean on the fact that it's already coming out of a spatial partition to know roughly where it needs to be placed for consideration in terms of the lighting algorithm itself. In other words, I don't think we have to do that work more than once. What I do think we need to do is we need to have some way of knowing how coarsely we need to subdivide any particular region, because sometimes certain areas may simply not have very many elements in them, and others might have a lot more number of elements in them as far as, again, those spatial partitions are concerned. So that's something that we need to kind of think through a little bit better, and I'm not sure exactly how I want to do that. So for starters, what I think I'll do is not try to be too fancy, and we'll just build this on the fly, but I want to keep an eye towards maintaining a spatial partition through the entire pipe, because I think that's probably the easiest way to do it. We know our game is sort of grid layout like. We know that we want a spatial partition for storage on the back end because we already have one, right? We've got, go ahead and open up the code here. If we look at how Handmade is working already way back in the early days, even just at, oops, I loaded Handmade Ray. That's not what I wanted. There we go. If we take a look at how the world storage is going, right, we've got this sort of chunked representation of the world where we pull chunks out of the world here, and those world chunks themselves are exactly one of these kinds of spatial partitions. So at that point, I feel like we could leverage how the world is being stored to give us a leg up on this as well. And similarly, for collision detection in the game, we're going to want something very much like that. So I feel like we could sort of be doing this in a single pass at some point, and as we weld those things together, I think we'll get speed improvements throughout the entire chain. So that's the only thing that I'm talking about here, is this sort of fact that we were doing chunking of the world already into these chunks here, where you can kind of see we've got these whatever this dimension is here, this chunk dim in meters, is creating a natural sort of gridding of the space that we've already partitioned things into. And so at that point, I think it remains, it's pretty trivial for us to say, can we sort of create a single unifying scheme where we store things based on this partition, we collision detect them based on this position, and then we light them based on this partition as well. Because that just saves a lot of extraneous work that we don't need to do. All right. So what I'm going to do for the time being is I'm going to, instead of trying to unify those before we really know what we're unifying, is I'm just going to say, well, we've got all these lighting elements in the world. I'm going to try and just sort of grid them up into groups, right? And I'm going to do that sort of just, again, based on a very simple bucketing scheme, nothing particularly fancy. And that way we can start with something pretty basic and work our way up from there. What I can then do is say, well, once we know what's going on with a sort of a group of nodes there, is I can sort of produce a little more information about those nodes and how much light enters or leaves them, and so on, right? So that's really all I want to do to begin with, and I don't have much of an idea of how big those should be or really what they should contain, but that's mostly, I think, all I really want to do for starters. So let's start with that. I'm going to go into render group. And at this point, I think probably rather than having these in render group, it might be a reasonable time for us to go ahead and add a handmade lighting file in here because, you know, we can. And the handmade lighting file, I'll cut and paste a little header in there. The handmade lighting file can sort of store all of our lighting stuff here. Let's see what we've got for that. I think it's all in here. We've got these in platform.h, and I could probably move this out. So if I take a look at what we've got in here, we've got all of this stuff, lighting boxes, lighting surfaces, blah, blah, blah. So there we go. Right. And in here, if this is stuff that needs to get included, I feel like we can just include it in here for the time being. And I guess to be honest, we don't really need to include it directly in here either. I think we could kind of move it into the other code as well. So I think the only reason is because of this stuff. Then the game render commands need to have pointers to it of the lighting box and the lighting point. So at some point, probably after we finish the lighting, we'll want to sort of isolate our render a little bit more, clean it up, and just kind of finalize all of our rendering stuff. At that point, I think would be a good point to sort of clean up the fact that this is leaked into the platform layer because the platform layer contains the renderer. We don't really need it to do that. We can have the renderer contained outside of that, and that's probably something we want to do a little later on. I don't want to do it right now because it's not really relevant right now, and it's not really what we're trying to accomplish right now, so it's a little premature to start doing stuff like that, but that is some architectural work we'll probably want to do a little bit down the road. That's like a day, well, not a day, but like one episode of Handmade Hero. So I call them days, but they're like 2 hours or whatever. That's one episode's worth of work. It wouldn't be a huge deal to do so, and so we should probably do something like moving that out. Anyway, so in here in handmade-lighting.h, I can pull out some of these calls that we had, and so that we can sort of keep them in a place that's a little more clear, and we can see where most of the lighting stuff is actually happening. So I'm just going to grab this out here and drop it into the lighting file. I'll pull this out as well, and then we can have something a little more sane. When I compile this, we're going to end up in a situation where, of course, we don't actually have a bunch of these things that we need. That's okay, because now I can just go ahead and include it in handmade.cpp. So let's go ahead and drop that in here, include handmade lighting. And this probably needs to be up above the people who are going to use it. So we're probably talking about something that's right under render group there. And then now we've got it sort of pulled out into its own file, and it's a little bit easier for us to kind of like concentrate on what's actually in there, right? Again, no real reason for this at all. It's not, there's no, I get asked about the file separation stuff sometimes. There is no rules or dogma that you need to follow for separating things into files. That's just the kind of thing that people go on about and clean code and these sorts of things that are not really real. They've never measured it. They've never proven anything about it. It's dogma. And so I always try to encourage people as much as possible to just be sensible and apply your own personal opinions to how you should separate things into files. Personally, I just separate things into files based on logical groups I like to look at. And what makes it easiest for me to get around the code. And that is exactly what you should do. There is no proven universal scheme for separating things into files, and anyone who tells you there is has literally does not have the proof. They have not done that because we don't even know how we would go about proving that yet. And so claiming that there's one right way to separate things into files is absolutely ridiculous. And I would never tell you otherwise. So I am doing that separation strictly because I want to be able to look at the lighting things as separate pieces that kind of live on the side, because I don't really want to have to like look at them intermixed with the rendering code, because it's kind of its own little separate pass. So at that point I felt like it would just be easier to have them in separate files. If somebody didn't want them in separate files, that does not mean they are wrong. That just means that they have a different preference for how they like to look at the code. All right. So taking a look at what we've got here, you can see that we sort of have no real multi-resolution-ness happening here. Oh, and that reminds me, in world mode here, we've also got this lighting solution. Let's go ahead and pull that out, because I think we should be able to pull that out here as well, right? So random series is not defined is the only problem in the platform layer, where this stuff has to get included due to the fact that it needs to know the size of those pointers. What I could do here is actually, you know what I could do, and this seems kind of compelling as well, is not really include this file there, and instead do something a little more fluffy, right? What I could do to make this a little bit cleaner is inside platform.h, because like I want to go this route anyway, maybe just say, hey, let's not really specify what these things are at the moment. Let's just say they're abstract structs. I don't know if we could do that with the textured vertex as well. We might be able to. For now, I won't. And I'm just curious if I could then say, at that point, once we come through here, we could do this in a little bit more traditional way, where in handmade.h we are including it along with the render group and so on. Again, this is just partitions it a little bit more nicely. Lighting solutions should have been in there. Why wasn't it? Oh, because world mode comes before render group. Why does that happen? Was that necessary? No, it wasn't. So at that point, all we really need to do is make sure that we also, inside our Win32 handmade stuff, since that stuff has to happen now, we can include the lighting. And that should, in theory, work. Hopefully, so that's, again, just keeping it a little bit more isolated. I haven't done anything to it yet. We have not done any changes to it, but we've just kind of pulled it out a little bit so that we're working on it in sort of a particular location. And now we can run it and see what we've got here. This is, you know, the lighting running non-multi-resolution. So now what we want to do is try to figure out a way to, again, group things together into aggregate elements and then do something sensible with the aggregate elements, right? That's what we're trying to do here. And I think, to a certain extent, we could, if we wanted to, probably... I feel like we should also be able to, when we split things into elements... I'm sorry, when we group things into elements, we can actually split our elements in half as well anytime we want to. Meaning, if we have a particular lighting element that's long and doesn't fit nicely into one of our buckets, we could split it in half. There isn't really anything that stops us from doing that, I don't think. We can have two like sort of virtual lighting elements that do not correspond directly to a single lighting element that originally came down the pipe. That is if we wanted to split an element up. We don't really want to split elements that often if we can avoid it, because splitting elements just adds more elements to the mix than we really want to deal with. So it's not desirable in most cases, but we could prevent having to deal with overlap elements in that way by actually just splitting up elements into smaller pieces. I think that actually works. Don't quote me on that, but I don't see any reason why it wouldn't. So we definitely are going to have a lot of options when we do this here, and so now the question is just, all right, how are we going to actually sort of break these into pieces? And the answer to that is I don't really know. One way to do it is to just apply a fixed grid to the world and let it go. Another is to try and actually sweep over the elements that we've got and figure out where a reasonable split is in them, and then split them to either side of that split, things like that. That's the more KD tree approach, obviously. And I'm just not really sure how I want to do that. I think probably... I think probably what I want to do is start with some coarse notion of... I think at the highest level, I want to start with some coarse notion of how the world should be divided. Probably, it's really hard to say. So traditionally what happens is, you kind of sweep over the elements and you take maybe the bounding box and you split it in half or something like that. And you just you sweep over the elements and you put them half into one side, half into the other side, and then you sweep again. This sort of a thing. I just don't know. I don't have a good feel for, what I'm not having any really good ideas about how to guide this process more intelligently than just like try some stuff and see what works. Because again, we sort of have an unusual, normally when you're dealing with ray tracing, you're dealing with fairly arbitrary shapes. And in this case, we know we're dealing with very highly regularized shapes. These shapes are all specifically cubes. And a lot of them are packed fairly densely together, so that they're not like overlapping in weird ways or anything like that either. So it's kind of hard for me to conceptualize because it's a very specific scenario, and I feel like there's probably some specific elements of the way these scenes are structured that should or could be exploited to create the spatial hierarchy in a way that makes a lot of sense for this particular type of scene. And that is what's sort of tripping me up a little bit. Meaning, I feel like there's probably something very smart to do here. I just don't know exactly what it is. But it's probably not, let's apply a 100% generic solution to it. Because this isn't a generic scene. Most ray tracing spatial partition algorithms are based on the understanding that you just have some arbitrary collection of triangles that represent some complicated scene with lots of heterogeneity in it, but we don't have that. We have a homogeneous world filled with cubes. So at that point, I kind of feel like we should probably be doing this in a cube-based way. So let's just do that. I don't know. I don't, since I don't have a particularly strong idea here, I guess what I'd say is let's go ahead and sort of break this into some number of elements at the top that we sort of prescribe. That's the minimum number of elements that we're going to consider. And then we'll just do something basic on the way down. I'm not going to try and overthink it right now because since nothing's jumping out at me, I feel like I don't want to spend too much time thinking about it before I just do something and get some information for how this sort of thing might go. So if we take a look at our lighting solution, what we want to do here is have some idea of like aggregate lighting information. So for example, if I was to have a lighting partition, something like this, then what that needs to have is it needs to have some information about, it needs to have some information about what's in the partition. And we know for every lighting partition, there's going to be sort of an array or something, or a linked list, or who knows what, but there's going to be a collection of elements that are in it. So something like a lighting partition would have some count, like a child count, and then it would have something like a pointer to the children, right? And each of those would have children as well, right? So you would have something like this. Each one of these would probably have a lighting box in it that had the information it was using, something like this. Only in this case, this sort of thing is probably going to be some kind of a union, because we would have two different situations. One would be where we have children that we're using for lighting, and the other where we have just an actual lighting box at the end. And so we'd probably have something more like okay, so we've got a struct here. This has a pointer to where our children are stored, for example, and we might do something more intelligent than a pointer in the future, but that's sort of a separate issue. So we'd have like a pointer to where the children are stored, and we know how many there are from the child count, but if the child count was 0, then we know we have something else. In this case, we would have our min and max bound, and then just the children, and maybe that's all we actually have in this case. Although I think we probably would also have more information here about the individual lights that were sort of coming out. I'm not sure. Maybe we might even sort of still have lighting box as our thing. It looks like we're using P and radius here, so. So it's hard to say. Maybe this would get welded in and this would just be a lighting box, and we'd have this sort of information here. In fact, what we could do here is actually call this pad. This pad could be the child count, in fact, I suppose, because since that's set to 0 and we've got a spare thing there, we would know that the children could be stored, the child count could be stored in that. Yeah, something to consider. So what we could do, is say, all right, couple pieces of information here. We know we need to have lighting box being down, then broken into pieces. We could just make it so that a lighting partition is just one of these, and then it just needs that extra pointer beyond just what's in the lighting box. So it seems like we could actually do that, and maybe we could even find a way to sort of sneak that in here. Yeah. So give me a second to kind of think this through, how this would actually work. Because those lighting partitions really just need the exact same thing as the lighting boxes. So maybe we use lighting boxes the whole way down. That does seem plausible to me. I think we would just need a little bit more here. The only thing that we're not getting here is, the only thing that doesn't fit in here is the index that would tell us, where our children are. But that's pretty simple to figure out, right? So suppose we were to do something like this. So in this case now we've got 6 of these. Like if we just take a look at this, we could easily pack the transparency in a more convenient way and keep this structure size down a bit, right? So even if, oops, that's not what we wanted. So even if we did have to expand that a little bit, we easily could and still keep it in a pretty straightforward fashion. So we know we've got 3 floats times 4 bytes per float here, times 2 elements, plus we've got 7 times 2 there, plus another 2, plus another 2, plus 1, plus 1, equals a 44 byte structure. So it looks like we have room for one more D word there. So this must have been a kind of a weirdly aligned thing, because 48 would be the normal number we'd be shooting for there. 32 would be ideal, right? Because then you get 2 per cache line. But at the moment, it doesn't look particularly like we would get that in there in any real way. Because we can't really get down to 32 given the hard requirements of the stuff that we need to put in there, I don't think. Although you could imagine overlapping these pieces of information in an interesting way that maybe does get you down to 32 if you were really squinky about it, right? Because there's an extra element stored in light index, which you use for differencing there. So I don't know, maybe if you wanted to be, if you wanted to do more work computationally, you could probably get it down. So since we don't care about that, then I suppose this is okay the way we had it before at the moment, right? So we've got 3 times 4 times 2 plus 4 plus 7 times 2 plus 2, oops, plus 2 plus 2 plus 1, which is 47. So yeah, this is just now a regular pad. So I think that gives us a 48 byte struct, which seems reasonable in terms of how these things would be aligned in memory. Again, a cache line is usually 64 bytes, so it would have been nice if we get down 32 for those 2 per cache line, but whatever. So the lighting box could easily have this information in it, and if that was the case, then we don't really need a lighting partition, right? We can just use lighting boxes the entire time and just operate on those sort of more directly. And then what we would do if we wanted to kind of go full bore on it is we'd just say, well, okay, so we've got a lighting box that is sort of our root box. And we start at that box and we just see where we, whether we intersect that box. If we do, we subdivide the box down until we get to the leaf nodes. And that would allow us to do, pretty straightforward sort of thing on it. Again, I'm just going to start pretty easy here and just use a standard spatial partition, and then we'll kind of look at how we go. So I'm going to go ahead and just treat it like that. I'm going to say that's the way it goes. And then I'm going to go ahead and make the render group there where it used to set the pad only. At least I think it used to set the pad. Where did it set lighting box? So here where it's setting this stuff, I'm going to go ahead and initialize these things. Child count to 0. That way it knows if it sees a child count equal to 0, it knows that this is a leaf node that can't be subdivided anymore, and off you go, right? Okay. So I'm going to start off by collecting some statistics here so I can kind of see what's going on during this process. So, because I want to start to take this a little bit more seriously and say, okay, I want to know how many boxes were considered during raycasting, right? So I want to have a thing that's sort of like boxes checked, or raycast box count, or something like that. So what I'm going to do in here is I'm going to go through, and in my lighting code where I was doing this before, when I sort of do my raycasting, I know every time I consider a box. I could also do something like raycast point count, number of points, number of originating points for rays, or number of times a point got used as an origin, and number of times a box got considered for intersection. And so what I want to do here is when we actually do the lighting test here, I want to start by initializing my solution to have those values set to 0, like so. And then at the end, I would like to say what they are. And what you can see here is that inside my compute light propagation call, then in here we loop over lighting points for emitters. And so what I want to do is say, all right, every time we get in here, this is a point count increase because we're saying we're taking this particular point and we're going to emanate something from it as a set of rays. So that's an increment there. We could also ask what the total ray count is. And so inside here, we know that we cast a ray, like so. I suppose perhaps a smarter way to place that would be to put it in the actual raycast call, like so. Because then we know every time we call this, we did it. Now inside here, when we go to do this lighting box computation, then we know that our box count gets increased. And I think that's probably all we really need to do. Now let me go ahead and include that other value here in the statistics that we just added. And again, I will initialize it to 0. So now when we run the code, I should be able to see some just really coarse-grained statistical information using the debug system. And you can kind of see where we're at, right? So what you can see right here is we're raycasting from around, let's say it varies, but it's somewhere in the 1500 range. And we're raycasting something like 30,000 rays, which leads to about 2 million box checks, right? So again, you can see why the CPU, as fast as it is already struggling with this amount, and it's running in real time, but it can't even quite hold 30 frames a second. You can see why this is occurring because we end up with a situation where the total number of boxes it has to check is starting to creep up on that number in a really nasty way. So again, if I just redirect your attention back here for a second, we look at this box count, it's around 2 million. Remember I said the total number we were going to have of cycles per frame at 60 frames a second would only be about 6 million. That means we'd only have about 33 cycles to test each box. We're using way more than that to test a box. So you can kind of see why we're already not hitting our 60 frame a second budget. That's really all you need to see is that number. So that number, we want to be trying to get 10x on or something, right? We want to produce a really significant dent in that number in order to sort of make our lighting get it more into the plausible range. Now, to be honest, I think we need more than 10x. I think we almost want more like 100x here because we're going to multiply the number of boxes pretty significantly. So we really need to make a dent in that, a very significant dent in that number if we want this to run acceptably on a modern computer. And this is a fast modern computer, so we have to make it run really well on this computer because older computers, that maybe are only going to run the game at 30 frames a second, we'll only have twice as many cycles to deal with, so it's still not really going to be a walk in the park either way. So we want it to be really, really fast on our computer because we know that we're kind of at the high end here. All right. So when we're doing our lighting test, what we want to do is focus on getting that number down. So what I want to do now is say, well, okay, so if we were going to do that inside this raycast here, what could we do? Well, like I was saying, we're looping over all of these boxes here. What I want to do instead is turn this into a sort of more hierarchical traversal of these rays instead. So when we're looping over this this set of boxes, What I want to be able to do is turn this into something that is going to be looping over a spatial partition. So if you imagine something more like this, where instead of looping over all of the boxes together, we can loop over well, in fact, I guess maybe I don't even need a for loop here. This may be something more like an if. And we can use this as a recursive function, potentially, although we may want to use it as a stack. So, we'll see how that goes in a second. We'll start with recursive, and we'll maybe switch to stack later on. But we're going to loop over, instead of all of the things in the entire solution, let's loop instead over something that's a spatial partition. So for example, what we want to do here is say, hey, why don't you pass me the lighting box that I should be using? So in here we'll say, hey, what's the lighting box to use as the root, or something like this. And so then what I can say is, if I hit the root box, which I guess maybe we're assuming that we have here. I don't know. That's a tough to say. So yeah, maybe we do something where we leave it in the same level of nesting that it was before. We assume we hit the, oops, that's no good. There we go. Too many keys. We assume that we're going to pass it some box to use, and so what it'll do with that root box here is it will assume that this has children, and it will loop over the children. So it'll go into, again, that lighting, this information here. And we could even, by assuming that the child count is modest enough, we could even expand this to a 32-bit index if we wanted to. We've got the room for it. I don't think we want to yet, but I'm just saying we could. So anyway, inside here we say the source index is no longer going to be 0. Instead, the source index is going to come from our root box, and it's going to be the first child index. Then we're going to say, okay, that root box child count is going to tell us how many to do. So we do it like that. And then we're going to proceed as we were proceeding before. We go through here, we do our raycasting, and what we're going to see is in here, when we hit a particular box, what we'll do now is say, okay, we'll actually go check the raycast in the box later when we would be producing the result. Instead of producing the actual result, in the case where we have children, we will just recursively call the function. So in this case here, for example, what we'll say is, okay, we want to get this closest hit back from a subcall instead. And for the moment, we're not going to worry about this path here at all. This was the unrolled path, which got a little faster. And to be honest, I guess we don't really want to keep this in the mix anymore. We know we can produce this. It only took us a couple seconds to do it before. We know we can produce that trivially, but right now we need to just focus on the multi-resolution stuff, and that function would have to, that unrolling would have to change rather dramatically either way. So in here, what we're going to say is, okay, raycast result is going to get one more piece of information. It's going to get the closest hit. Like so. And so in here, when we're coming over these, we would produce the closest hit. And maybe what we do here even is say, okay, when we know the closest hit, let's instead of tracking all of the result information, let's instead, let's not do that. Let's go ahead and produce this information in a slightly different way. Let's go ahead and produce this information at the end only, right? So once we know who the hit actually was, maybe we just return the index of the box and we don't return any more of this information. So that all can be taken care of outside. So given that, maybe let's just do this just real quick. Let's make sure that this will still work if we do it this way. If we change the return structure a little bit here, and we say that raycast result just does U16 box index. Right, that's all it does. Or maybe it produces the pointer. So that's it, right? That's what the the raycast actually tells us. It doesn't tell us this information. So this stuff has to be found in a different way. After you do the raycast, which happens right here, then what it does is it has to produce this information in a different way. So what it'll do is it'll say, well, okay, I needed this piece of information, so what I can do is just get it like that, right? Pretty straightforward. And all I really need is the box surface index here. I need to note this actually doesn't need to be done this way either, because now we would have this as a null pointer if nothing got hit. So actually what we can do, now that I think about it, is this can be simplified slightly as well, which is this can just be if ray box. Right? All right, so then we need to know the point count result, which again is going to be this piece of information here. Like so. So that hit point count again is just the ray box surface index, like so. So this is really I guess one more piece of information that we need. So just reorganizing that code slightly to use this piece of information. Looks pretty straightforward. And I think that's it. Right? Oh, no, one more thing. The ray p here. So we know what we cast, so we should be able to do this directly. Since we do the raycast from the emit p and we know the emit direction, then the t along the ray should just give us the ray hit point. So off we go, right? This piece of information right here. So I think that's it, and that should just work, hopefully. All we have to do is actually fill that information out. This is no longer get set. We can ignore that for the moment. And then in here, what we would do is when we track the closest hit, we could also just store which box surface index we were on and which source index we were on. I think that's it, right? So box is an undeclared identifier here. That is correct. Although we could just do lightning box hitbox equals ray.box. That way you can just say hitbox everywhere and we know what we're talking about. And that is off of the T-ray. So unfortunately, that should probably slow us down a little bit. It didn't really much, to be honest, but probably a little bit. Because again, we're probably not quite as efficient as we were. It depends on the circumstances. Because there's still a little more fussing going on here than needs to. But I have to do that temporarily, at least, in order to make sure the raycast can now be called sort of as a recursive function. So in here, we're going to say, all right, let's take the lighting box, that's the root box. Now we'll switch back to calling it in this fashion, like so. And now what we can do is when we get down here and we find a particular box, what we can do is say, well, let's go ahead and call this this function sort of recursively. And what we'll do is, instead of the closest hit being reinitialized every time, what we'll do instead is say that the closest hit gets passed in, right? So now what we can do is say, well, we start with the closest hit value. That's whatever gets passed in here. If you don't specify it, it'll be initialized to the nothing value. But when we call through here, then what we'll say is, well, when we get a closest hit value back from anybody, we remember it, right? So what we can do here is say raycast result, or actually I guess we can just do is say our result equals call the raycast again, with all the same parameters that we were calling it with before. And again, this is why I say we want to probably turn this into just stack based, because we don't want to keep duplicating this work and pushing it on. There's no point to it. It's just a waste of everyone's time. I'm doing it as a recursive function at the immediate moment because that's just a simpler way of writing the code first, but we probably want to expand it out later because this is a performance critical part of the code, and we're going to want to massage it as opposed to just letting it be written in the simplest possible form. We need it in a more performant form. So once we do this, we get our raycast result back. We do it like so. So what I need to do is determine, do I need to do further raycasting or don't I? So in the case, and it looks like here too, what I want to do is for closest hit. What I'd like to do is actually make that just probably be part of the raycast result that I'm returning. So I want my T-ray to be part of the closest hit. What I could do is actually also make all of these just operate on the same raycast result. In fact, now that I think about it, that's probably the best way to do it. So the result is just something that we're going to fill out here, right? And what I'll do is say, okay, we're not going to touch any of this. We're just going to say that we pass this in here. We can initialize it this way. In fact, you know what I'll do? I'll just make one of these. Works the old way. So when we call this, we initialize the raycast result by saying the box equals 0, which means there's no hit. And the T-ray value that we're working with is F32 max. We don't need any of the other information because it won't get used unless the hit happens, right? Then we call raycast recurse. With the root box. And the result that we're trying to produce, we go ahead and produce that result, and we're off to the races. So closest hit is now going to be result T-ray. And you can see now that we're updating that information here like so. So what we want to do here is call raycast recurse directly, and I want to move this raycast call down. There we go. So in the case that we find that we actually hit one of the surfaces of this box, then what I want to do is I want to call the recursive check of the box. And furthermore, what you'll notice here is I don't really want to be inside this check anymore. Because once I've determined that I'm going to recurse a box, I don't need to recurse the box anymore, right? So if I hit one side of the box and go, I'm going to go down into this box, then this doesn't need to occur anymore. I'm done at that point with what I was checking. So yeah, I shouldn't have to do this because technically speaking, I can only hit one side of the box and we're not checking the exit side of the box anyway, so it shouldn't actually ever happen. But it also means that if we happen to hit axis on axis 0, we could skip the checks for axis 1 and 2. It just speeds us up a little bit. I guess now that I think about it, we can probably actually just do this period. If you hit one of the corners, we don't need to check any of the other corners of that, obviously. That's just kind of, you know. a property of a solid. A convex solid that you only check the front faces of, you can only hit one of them with a ray. That's just common sense, right? There's no... A ray is going to hit it at a single point, and that point cannot be on more than one face of a convex solid. I would have to be in a concave solid in order to enter and exit the shape. So that was probably something we could have done earlier anyway, and just didn't do. So if the box in question has a child count, then we will recurse that child count. The way we'll recurse the child count is by sending all of the same stuff through. But now we're going to use this box as our source for getting the information, and we're going to pass it the same result that we've been working on for it to fill out, right? And I think that's all we really need to do right now. We can get rid of this now because that's sort of done in line. And I think that's everything. Science. Unsigned mismatch. I don't really understand why this integral promotion does this way. It's kind of a little bit weird to me that it does. I've never really been at one with C's integral promotion rules. They always seem a little bit not what I want. But, you know, it's fine. It doesn't matter. So this is an arrow, and so are these. This no longer has to be in equals because we're just operating on it directly right here. So that's good. And I think that's everything we need. So all we have to do now is actually have one of these sort of root boxes, which we don't have yet, right? All right. So what we need in order for this to work is actually building a spatial partition. So I'm going to make something here. A function that will do exactly that. Here it is. And so what I'm going to do is, before we get into any of this nonsense, I'm going to go ahead and say, okay. I'm going to print out both of these because now we might expand the number of boxes and points, right? So anyway, I'm going to say let's build a spatial partition for lighting here, and let's have that go ahead and build up these things. Now, the way that I'm going to do that is, again, very straightforward. Here we've got, I'm just going to start by saying everything's in one node. So it's going to do the exact same thing it was before, just to make sure that our routine is working properly. I'm just going to do the exact same thing as we did before and verify that we can still get the lighting out because, like I said, baby steps with code that's complicated like this. So I'm going to go ahead and create a lighting box. That lighting box is going to be whatever the next box is. And this box is going to be my root box. So I guess I can also do this. And this box will have a p-value of 0, 0, 0 and a radius value of... you know what I just realized is we don't have a check for whether we're inside the box, which we would also need, right? So there's two ways we could do this, and And one of them is pretty clever, and I'm just wondering if it's a little too clever or what. So we know we want to check boxes that the ray passes through. So that's the check that we're already doing. What we don't currently do is go, if the ray started inside this box, then we need to subdivide the box. We don't do that yet. So the problem here is that, we don't really want this routine to have to think too hard about that. And so one thing we could do is make that work on the back faces of the cube. And I'm just not sure if the checking, in other words, if we said the radius was this, all rays inside would always hit it. They would hit it as they exited it instead, and it would trigger it to work. I just don't know whether the check for being inside the bounds works or not. So I'm going to have to work that out, but it's just, I'll explain that in a second. It would be kind of cool if it worked, is the only thing. So instead of setting this to anything real, again, I'm just going to set it to something that causes all of them to be checked, right? And off we go. Okay, so let me talk a little bit about what I was just saying, and I guess I don't really know because we did some optimization here on this. So if we set the radius to be negative, then some interesting things occur. What ends up happening is that the locations move backwards to the opposite sides of the cubes. And the only thing I'm not sure about is whether those radius values create a problem here. Yeah, so you can see the problem that we would have, which is these values need to be absolute valued. That's about the only thing that it looks like we've got a problem with. So really it looks like if we just do the absolute value of these two, if we just do this, I think that's all we need to do. We'll find out in a second, though. I might be completely full of it. So here we go. Looks like we're doing okay. So let me just say what I was doing there and why I was like, okay, this is a little bit overly clever. Sometimes clever things are fun to figure out because, well, they're clever. Oops, did I put day 423 up here anywhere? I didn't. So anyway, what I was saying here was let's suppose we have one of these cubes that we're talking about. So what we had optimized for before is, and not even optimized, but actually wanted, was we know that we're always raycasting from outside because we're trying to gather light from things that are away from us. So all we needed to go was let's take the things that were, sort of directly facing us and ignore these faces here, and let's produce a hit, right? Let's produce a hit that tells us what's going on. The problem is, once we start talking spatial partition, now there are much larger volumes, and some of them may include the point that we're casting from, and we need to test whether we're inside it. So what I was saying is, well, okay, this won't work for that, because if I'm inside it and I'm going this direction, all of the faces that would have been front-facing to me are behind me, and I'll throw them out as not being valid hits. But instead what I can do is say, oh, if I set the radius to negative, then my front faces actually become my back faces. So this face gets moved to here, and I will hit it, right? if I was inside. In fact, anything that was going to be passing through here will hit the back faces. And furthermore, I know that I'm not, even if I was outside it, passing through, I know that I have to pass through the front faces and the back faces, so I know I miss no rays in this case. Checking against the front faces of a cube only tells me whether or not I've hit anybody who... checking against the front faces of a cube only tells me if I enter the cube, but checking against the back faces tells me whether I left the cube, right? And so for a bounding volume, I want to know whether I could leave the cube, because any ray that starts inside or outside that passes through the cube will have to leave it. But only things that start on the outside of the cube have to enter it. Does that make sense? So this was just a cheeky way of doing this that I think holds up. It's not so clever that I won't do it, but we'll see if that comes back to bite us in the backside. Again, this seems to be working okay, so let's just say all is well. So what I want to do now is try to figure out, what to do here for building a sensible spatial partition, right? I think what I'm going to do first is just do something relatively crude, and then we'll work on expanding it. I don't know how much time I have left. You know what though? The bot probably does. So we have a half an hour, so yeah, I'm not gonna, what I'll try to do is build a basic spatial partition first that's not particularly good, and then what we can do is tomorrow start to think about how to build something that is maybe good, and go from there. So here is our build spatial partition call, and what I want to do is, yeah, again, make this a little more sensible and systemic here, and we'll kind of go from there. So we've got some issues that we have to address, and I'm not sure exactly how we want to address them. So here are our problems. Right now, we don't have to take a hit on indirection in order to iterate, right? When we iterate through here, we just go through and say, okay, let's go ahead and raycast these boxes, and we get the sources by just reading them out linearly. There is no indirection here at all. We just say, take the index, and we directly read it out of solution boxes. If we are going to spatial partition, we have a problem. Our boxes are stored continuously here, right? And, you know, they're stored in just a big array. There's no indirection. They're one right after each other. When we go to spatial partition them, we will have to either rearrange them in that array, which involves a lot of memory traffic to put things into their correct locations, in order to keep them so that they are contiguous per sub box. Or what we would have to do is have an indirection that basically says read an index and jump to that location to figure out what it is. And it's like, that's one of those things that you really just don't know what the right thing to do is. I think I'm going to go with what I'm going to do here is I'm going to test the indirection speed first, and I'll see how bad it is. I think that's what I'd like to do first. So let me go ahead and try that. So at the moment, we are running around in the steady state. We're getting about 35 milliseconds here, something like this. If we take a look at the profile, right, you can see that we're getting somewhere in the order of 148 million cycles being spent on the light propagation computation. Okay, 148 million. I want to make sure I don't take an appreciable hit for this, and assuming that I don't, we'll probably use it. So I'm going to go ahead into the lighting solution here, and I'm going to add an indirection. And what we're going to do is we're going to look up into this box table every time we go to actually reference a particular box. So inside here we have lighting boxes. You can see that there's a few places where we do this. So we do one there, we do one here, we do one here, and we do one here. Yeah, so output lighting points that loops over the boxes. That one can still do it because it's just looping over the raw boxes themselves, and that's fine. So that doesn't really affect anybody, no real issue there. And furthermore, we can make this do loop over the commands light box count here for the time being, so it won't actually loop over the other boxes, which don't really have light indexes associated with them yet, right? So that's fine. There we go. So everywhere we do solution boxes now, what we want to do is just have a little inline function here that's like get box. And have a box index here, and instead what this is going to do is return boxes plus box index, right? And you see what I'm talking about where it's indirected. It's a little nasty, right? It's adding some work there that we really rather not do, and we just don't know how much that's going to confuse the processor and its caching scheme. All right, so from now on in here we need to do this. And I think that's all we're really talking about. So then all we have to do is initialize this into something that actually just mimics exactly what we have right now, and we should be good to go. So for example, in here I can just do a for-i loop. Like so. Actually, I guess this could be U32, it doesn't even matter. What? Oops. Yeah, didn't want to do that. All right, so all I did was build an indirection table that literally does nothing. And so, yeah, and hey, that didn't work at all. So that's not great. What did I mess up there? Because I wanted to just make it so that it literally doesn't do anything weird. So the box table is initialized to... Oh, yeah, this has to be after we're done. For the moment. Because otherwise it won't get this one. So that's fine. And honestly, it looks like that didn't have any effect. So actually adding an indirection there does not appear to have been a particularly problematic situation, it's still hovering around pretty much exactly where it was. So yeah, if it had any kind of a performance impact, it was not a significant one, so I don't feel particularly bad about that. So the reason that I want to do that then, as the solution rather than moving things around, is it will reduce the memory traffic to just reorganize U16s, and also it means that we can include the same light box in multiple, like if we want to, we can put a box in more than one hierarchical box, right? So now we have complete freedom to play with our spatial partition because the same child node could be put in two, it can be completely loose, basically, if we want to be, right? The same child node can be placed in multiple places because since there's an indirection table, that indirection table can point to something twice. It could be a one-to-many, or I should say many-to-one relationship in that case. Okay, so once we've gotten that, now we can actually build an actual spatial partition if we want to. What we can do here is say, well, all right, let's just do a standard thing where we subdivide these boxes, and we'll see what happens, right? So what I'm going to do here is I'm just going to say, let's do something. It's probably, split box is probably the wrong call. What I probably want to do is say add overlapping boxes. And what I want to do here is I want to pass a lighting box that is the container. And then I'm going to pass a range of boxes to check, and anything that overlaps the container box, we will add to the container box, right? The dumbest possible thing. So I'm just going to say like first box index and box count, as we've been doing. And here, so what I'll say is, okay, let's loop through for our test index, for our box index. First box, let's do test index. First box index, test index is less than first box index plus box count, right? Plus test index. So then we have our test box, which is just whatever, oops, that's the solution here. So in this case, we have a call that'll just loop over all of the boxes you give it in a range, and then it'll pull out each of those boxes. And then all we have to do is say, okay, do these two boxes overlap, right? So does the box that we're testing touch in some way the box that we're overlapping, right? So what we want to do is say if boxes, or like we'll call these like radius boxes, right? If radius boxes overlap, and we'll say container P, container radius, test P, test radius. Then what we need to do here is we just need to say if they overlap, then what we're going to do is we're going to target we're going to go ahead and target, I just thought of something else interesting actually that I hadn't considered before. We're going to target the box the box that we just tested. We're going to put that into the child list of the box that we are adding to, right? So we've got this container box here, and it needs to have its child count incremented, and it needs to have it needs to have this test box's index added to it. So it's going to add to this container this test index. That would be the entirety of the overlapping box pass. And so what we can do here is we can just say, well, you know, as we go through it, producing boxes that subdivide the space, what we can do is create new boxes, add the overlapping things to it, and just recurse down. So we'll basically say we'll sweep through all the boxes that we have, we'll split them into at least 2 new boxes, add them correctly to whichever box, to the box to which they belong, and then from there we'll continue subdividing, right? So that seems pretty straightforward, nothing particularly weird there, and we'll just stop when we get to some small number of boxes contained, and that'll be the last subdivision we do. So that seems fine to me. What we need to do is actually make that happen. So let's figure out how we're going to make that happen. Even right from here, what we would like to do is have a tighter bound here, potentially. But yeah, we'll get to that later. All right, so let's see how we're going to do this exactly. So I think what I want to do here is say that after this sort of special case startup, where we've created our initial box with everything in it, then from then on, I think we want to do something where we start subdividing. Where we start subdividing, yeah. All right. So when we do spatial partition, I'm going to do a call called subdivide box here, or let's just call it split box. And I'm going to pass the box. This is the root box and the solution. This code is going to be really crappy because we're just playing around with it now. So I'm not going to try and actually think through how this is going to be fast or what it's going to do. It's just going to be crappy. That's just the truth. All right. So then what I want to do is say, okay, I've got this box that I'm trying to split. So this is my splitting box, let's say. Or maybe this is the parent box. And what I want to do is produce child boxes. Something like this. Oh, well, maybe I don't have time to do that. So let's not do that. There we go. All right, so we are currently testing against the spatial hierarchy. We are just not building a spatial hierarchy that includes more than one parent node, so it's not going to do us any good. Tomorrow, what we can do is we can come back and actually build a little bit of spatial hierarchy there and start to tune it to see if we can get some better performance out of it. And specifically, we want to try to get to some better performance where we have a lot more light sources. So for example, if we take a look here, you know, this isn't the worst frame rate in the world, but it's because we're using a subset of the scene. If I was to go back into Handmade world mode and where we do our screen stuff, where we, you know, have something here, if I was to make this a very large number, where we're actually creating a world that's more representative of the number of elements that we would actually have here. Oh, I guess that's even more than we can do at the moment. I think that's probably because we don't actually have a good creation call there. But you can see how slow this gets once there's more stuff in the world. So that's the part we're really trying to tackle more than anything else, is that slowdown. And so what you can see here is that when we get our lighting solution scaled up a bit too high, it looks like this even, did this wrap? This wrapped the total value. That's how many boxes there were in the world. So we're more than 64,000. Ugh. That's tough. So I wonder if we're going to have to expand those even to 32-bit indices, which is pretty tough. If we were going to expand it to 32-bit indices, the places where that would have to happen where I care about it is like right here. That's the part that's kind of a little bit bad. But yeah. I mean, I am okay with it, but it's not my favorite thing in the world. But it looks like we will have to do that. So I guess that's what we'll actually first do tomorrow is we'll just expand that. Because that's going to be too many of these. Assuming that is actually what's going on, which I assume it is. Although I'm not sure why we didn't hit an assertion there, because it should have asserted on trying to add more than the number that are actually allowed to be in there, which I thought was... yeah, I'm not... That's a little confusing. I'm not sure I understand why that number is doing what it's doing. So if I come up here and I take a look at the call that actually pushes one of these on here, quad bit mass purchase array, we get these cross normal direction. Where's my push cube call? Here's my push cube call. So this right here, what is light data width? So as long as light data width is still less than 64,000, it should have asserted there, which means we're not passing more than that number of boxes. So why was that number so low? You see what I'm asking, right? Like, why was that number so low that was getting printed out there? I'm super confused about that. Because it says that the total number of boxes is 358, but we know that couldn't possibly be true, could it? Oh no, I guess that could be true. Never mind. So I guess we're fine. We're fine. I panicked for no reason. So I turned the lighting off temporarily. I'm going to go ahead and move to the other area here. So looking at here, yeah, so I guess the box count really isn't that bad. So that's okay. Never mind. Whew. I panicked for no reason. All right, let's go ahead and go to the Q&A, because I would really like to keep that under so that they can be packed a little more tightly for this routine if possible. At least that's my preference. So yeah, so I'm hoping that we don't actually have to go up above the 64K boundary. Not to mention the fact that that's a heck of a lot of lighting points to be considering. Yep. Can you try lighting as it is in a release build? Yes, I could. That might take a second. So in a release build, we would have to get rid of all of these. So in a release build, we're like this. And I don't know, even that might not really be getting rid of all the stuff that we need to get rid of, so I'm not 100% sure. But there you go. So, I mean, it's still, you know, again, it's still, that n squared is just too slow. It doesn't matter what mode you're in. It's too much for the computer to handle. You know what I'm saying? So, yeah, that's just not going to happen. But that's what it'd be like. I can also try, if you wanted to know what it's like when we don't have a lot of rooms. So frame rate wise, that seems fine. You mentioned something with the need to handle concave and convex solids differently when raycasting due to, I believe, the possibility of entering and leaving a single face of a concave solid multiple times. Any chance you could explain a little more how this could affect us if we have convex solids? Sure, it's not a single face, it's just the object itself. So there are certain properties of convex solids that make them different from concave solids in the case of raycasting. So, you know, for certain things, concave solids and convex solids, they don't differ. In other things, they do. And so it depends on whether the algorithms you're using happen to depend on the properties of concave solids, of convex solids or not. Raycasting happens to for most optimizations. The reason for it is as follows. Here is a convex solid. Here is almost the same solid, but now I've made it concave. So the problem here that we face is that when we're raycasting against these, and let's say I take the exact same ray, so this is the ray in space. When you take a look at a ray and you say, what faces of an object do I need to consider when raycasting this ray against a solid, a convex solid has the property that in order to enter the solid, you must enter through a front face. That's just true of convex solids because you know for a convex solid that a face that does not point at you always has some other face pointing at you that comes before it, right? So for example, here's a face that points away from you, and you know that the entire region where a ray could be hitting this face right? No matter where it is, there's always some other face there that is pointing in a facing direction to whatever the ray is. And there's never a way to construct another ray that could hit this face but not one of the front-facing rays. The way to think about this is that any way that I might split this into two sets of faces requires me to pick two vertices, right, and split along the plane that connects those two vertices, right? That is the only way I could possibly ever split this into two sets of faces without splitting a face in half, right? So all of these faces are on one side of the split, all these faces are on the other side of the split. For a convex solid, I know that once I have performed that split, for any face on this side, the angle of the face relative to the split plane is always it's always strictly on inside the bounds of this face's angles, right? So for example, if I took a look at right here, this split point, and right here, what I can do is I can take this direction and this direction, which are the two face directions that are there, and I know that nothing on the other side can ever be, right, any further inside than those two angles. They can never cross past that winding. So all of these facing directions are all outside of the range specified by these two. Imagine it in a circle. I took these two, here's the down one, and here's sort of the out one. When I split the faces, I know that I've produced a set of angles of faces that fall strictly within this region and one that falls strictly within this region. And there's no overlap. So when I ask about a ray that's coming in, and I say, what are the faces that I could possibly consider here? Well, I know that if I was to go ahead and split the ray in this way, and say I'm only going to deal with the front faces here, right? Then what I know about convex solids is that those front faces create a single unified front, right? Whatever they are. Those front faces produce a range that produce a single unified front such that there is no other face outside of the range that might be, there is no face on the other segregated part of the object that whose direction could fall in that range, right? So what that means is I have a clean split, and I know that my first intersection, my earliest intersection, will only fall inside that range, because no face out here could even be involved in it, right? For a convex solid, the same is not true. For a convex solid, when I split the faces, if I was to split them into front faces and back faces, I don't have a continuous range anymore. So for example, if I was to split these into front and back faces relative to this ray, I would get this one and this one, but then I would also get this one. So now there's a hole in the range where this back face is occurring, right? Does that make sense? What ends up happening now is I end up in a slightly weird scenario where now I cannot consider my object to strictly be based on the front faces for purposes of total consideration of what's going on in this volume, right? Because I don't necessarily know what happens in these external areas. So if I was, for example, trying to test to see whether a ray passed through this particular object, right? And furthermore, whether certain things inside the object needed to be tested, I'm at quite a bit of a disadvantage because I don't really know until I do testing on all the faces what the ray really did, right, relative to it, or where a point really was relative to it. For example, let's say I gave you a point, right? And I said, does this point, is this point inside or out of this concave object? Well, if I wanted to know that information, well, you know what, I guess... So there's a couple of different ways to think about this. So here's what I'll say. In the case of the specific thing that we happen to be using it for, where I said the back, I'm just going to test the back faces to see whether the ray ever passes through this thing. In that particular case, I think I may have misspoke when I said that the concave objects couldn't use that property, because it might be that they always actually also can. I'm scared to say that because I don't know if it's actually true. But the thing I was about to say isn't necessarily as relevant. Let me finish. So if I wanted to know whether or not a point, let's say, is inside one of these volumes, in the case of a convex volume, all I really have to know is whether or not I am on the inside of all of the points, all of the planes, right? So if, you know, all of the normals of these faces all point in towards me, then I know that I am that I am completely inside of it, right? So because I know that there's always a perfect classification of all of these of all of the planes, and if I'm on the same side of all of them, then I know that I'm inside the solid. Similarly, if I want to test for outside, I can do the same thing. If I want to test to see if I'm outside, all I have to do is find a single plane pointing that I'm on the outside of, and I'm done, right? Even just one plane telling me I was outside the solid, and I know that I'm not outside the solid. And I know that I'm not inside the solid, right? For concave, things get a lot more complicated. For concave, I can't tell, because I'm always going to be outside of some part of a concave shape and inside of another part of the concave shape, no matter where I am, because it's concave. So what I have to do is I have to go ahead and say, well, let me count how many crossings I have in a particular direction to see whether I was inside or outside, right? Like I say, well, okay, I crossed it once, I must be inside, I cross it twice, and now I'm outside, right? So things often get a lot more complicated when you go here. But when I'm just thinking it through, the concept that I literally said, which is that if this is what I said, I think you may be right to call me out on that, because I think that may be true for concave. Because as long as you test the back faces, like the way we've got this routine set up right now, it wouldn't fly. Because if you look at the way we have this routine set up now, we only ever test 3 back faces. We just assume that there's only 3 back faces because we know how the shape is. And so it's, you know, it's highly optimized for the fact that we know exactly what we need to know about the cube. So this is like highly optimized to just check these 3 back faces we know are the back faces of the cube, and we know it's concave and all this. It's all optimized to take all that into account. But if you just had a generic shape, I think you might, if it was closed, as long as it's closed, meaning it doesn't have holes in it. How do I say that? As long as you know that it actually produces a solid with no cracks, right? So if it was cracked, so like for example, let's say, you know, this is a closed convex solid. Right? Let's suppose it was cracked. With a solid like that, now there is no definition of inside or outside of it. So you like forget those kind of shapes temporarily, because I don't really want to talk about those, because you'd have to start coming up with what you mean by inside or outside of it, right? So ignoring that, if we just said, well, we just want closed convex solids to work. I think it still works. I think if you have a ray and you just test the back faces, right? Oops, that's a front face. So if you just test the faces that are back facing to this thing and you hit one of them, then you passed through it. And whether you're inside or outside, I think that works. So I think I shouldn't have said that. I think that technique would work for concave as well. We don't need it to, so if I'm wrong about that, it's okay, because we're only doing concave anyway, and I promise you it works for concave, because I don't see any way it could fail with concave. I'm sorry, I promise you it works for convex. For concave, thinking it through here, I guess I don't know. It seems like you could just apply the same technique. I think it would just work. So never mind. Never mind. Enyo and Ev, why do we skip the part with placing cubes over entities such as trees in the hero, and also they should receive light in some way, right? Yes, we will eventually do that. We just don't. It doesn't matter right now. So I'm just focusing on getting the lighting working, and then we can worry about how we want to place it. Because we will do that when we do the world generation stuff. We'll play with that a little bit more. We noticed your four color and military are color coded. What are the values? Yes, they tried to sort of make them similar. I don't know what the color is because it doesn't print it out here necessarily. But in 4Coder you can see them. So I believe this is probably the color that you're talking about, and so in Milton doesn't have, I don't think, RGB sliders, so I couldn't set it directly. So what I did there is I just tried to get it as close as I could. Okay, so I think that's it for today. Tomorrow we'll finish building that hierarchy, and then we should be good to go on playing with getting the lighting up to a reasonable speed. And we also have to end up making a decision at some point about whether it's going to be on the GPU side or the CPU side, because that's sort of a separate issue as well. All right. Thanks, everyone, for joining me for another episode of Handmade Hero. It's been a pleasure coding with you as always. If you would like to follow along with series at home, you can always go to handmadehero.org and pre-order the game. It comes with the source code as it is every day after we finish it, so you can play around with it and do your own experiments. We also have an episode guide you can go to if you want to catch up on old versions of the series, and we have a schedule bot you can go to if you want to find out where we're going to be live. We will be back here tomorrow for more Handmade Hero. Hope to see you there for that. Until then, everyone, have fun programming, and I'll see you on the internet.